Organic chemistry, and we're kind of in the home stretch here of organic and sort of our last organic type groups that we're going to be discussing. We talked about last time our carboxylic acids. So remember, when we talk about our carboxylic acids, they do have that carbonyl functional group along with the OH, and again, that is our carbon-oxygen double bond with the OH group there. That is the functional group of a carboxylic acid. That group, as we talked about, basically comes at the end because, again, it does have that hydrogen that's there. So it does need to sort of always be at the end. And that does affect sort of how we go about naming it. So as we talked about last time, there's kind of two ways you could, I guess, look at naming our carboxylic acid, but it pretty much will end with OIC acid at the end. You could drop the E from the alkane and put the OIC acid. So, if you had something like this, has one carbon, two carbons is really based off of ethane. You could drop that E really, and this becomes ethanoic acid. Now, a couple things with naming our carboxylic acids, because this group always has to be at the end, unlike a lot of sort of functional groups, we don't have to give the location of where that carbon-oxygen double bond is, like we do, say, in a ketone, or if we have a double bond or triple bond, where those guys are located. So we don't have to do the numbering part in the name, but it's important, as we talked about last time, that this carbon here will always be carbon number 1 in purposes of numbering other sort of groups that are attached there. So also there's a couple, like for example, this one, ethanoic acid, it's also acetic acid. It's basically the main part of vinegar. And a reminder that sometimes in formulas, like an acetic acid, that carboxylic acid group is sort of written in this arrangement. So again, if you see a formula that has sort of that arrangement, it is referring to the functional group, again, for carboxylic acid. And that's basically what it translates to. So same thing, pretty much like all other organic guys, we're looking again for the longest continuous carbon chain. That group there will be either on the, I guess, left-hand side or right-hand side, I suppose, one side or the other. And again, that carbon-oxygen double bond is carbon number 1. Alphabetical ties everybody else that's attached to their groups. Again, those guys will be numbered accordingly based on the carbon-oxygen double bond. So let's talk a little bit about some properties of these carboxylic acids. A lot of times carboxylic salts are used as preservatives and flavor enhancers in soups and seasonings. Carboxylate salts are basically carboxylic acids that basically don't have the hydrogen part of it. So this is basically what that is. Remember, salt's really like an ionic compound, so this sort of situation is sort of happening. But one very important property for carboxylic acids is actually those two groups that make up the functional group. And it gives it some really important sort of properties. First off, as we talked about, the carbon-oxygen double bond, this carbonyl group here is a polar group, with the carbon being more positive, the oxygen being more negative. Unlike a lot of organic sort of compounds and functional groups, in addition to that group, the carboxylic acid also has another very polar group, which is the OH part. And that OH part is, again, the same sort of thing that we see in water, also a polar bond between the oxygen and the hydrogen, being negative more on the oxygen and more on the positive. What that does for carboxylic acids is essentially gives it multiple locations where it can really participate in kind of hydrogen bonding. And if you remember, hydrogen bonding is that intermolecular force we've talked about. But one important aspect of the ability to really hydrogen bond and stuff like that is it's a relatively strong intermolecular force. And if you have the ability to do that, usually in terms of things like boiling point, melting point, those things are typically high in those situations. And that's because it takes a lot of energy to break them apart. So unlike, say, like an alcohol, for example, which up until now, an alcohol has sort of been the highest in boiling points and melting points because of that hydrogen bonding it can do with itself, for example, along with other things. But now when we get these sort of carboxylic acids involved, there's a lot of interaction that can happen between, say, two carboxylic acid groups on different sort of guys or compounds. Again, the negative here can go here. This guy, again, could sort of hydrogen bond here. This guy also could do some hydrogen bonding over here. So there's a lot of bonding that can occur between really a carboxylic acid in itself and also with water, as we'll see here on the next slide, as it can do those hydrogen bonding. What that's going to really do is, up until this point in terms of boiling points and melting points, our alcohol has been sort of the highest in terms of boiling points and melting points. On the other end of the spectrum is like our alkanes, which really can't do much. But we are going to get carboxylic acids really ending up being much higher than that because it's able to really form what is sometimes referred to as a dimer with itself. It can actually hydrogen bond with itself and make this really two sort of strong attraction forces with itself and allows it to have a very high boiling point. Because of those multiple polar groups, it also very much increases the solubility in water. It allows it to interact well with water through hydrogen bonding, with 1 to 5 carbons being very, very soluble in water. So again, these are all hydrogen bonding that is occurring. And again, it's going to increase the solubility because the water has the ability to interact with the oxygen on the double bond. Water also here has the ability to interact with the hydrogen on the OH bond. So it gives it multiple places where a carboxylic acid can interact with water, and that is definitely going to increase the solubility of a carboxylic acid in water because of that. So really, solubility in water all has to do with the ability to hydrogen bond. So if something has the ability to hydrogen bond, as long as it doesn't have a lot of carbons, for the most part, these organic guys will be pretty soluble in water. So rough estimate for most things that have the ability to hydrogen bond, 6 or 5 or less carbons, usually fairly soluble in water. Again, if you get more than those type of carbons, more than 5 or 6 carbons, and they just keep building out the carbons, as we talked about, I think, a while back, we're building up the sort of non-polar part of the molecule versus that one spot, which is, or in this case, 2 spots, which are kind of polar. So usually with organic stuff, as you build out those kind of carbons, and hydrogen part over 5, 6 carbons, again, it just gets in the way of the ability of this part to interact with water. But on smaller ones, they're very, very able to bond very well with water or be soluble in water. So things that can hydrogen bond have that ability to be very soluble in water. So up in this point, things like our alcohol has a very high boiling point and melting point, and also very soluble in water. And then also our carboxylic acids, again, at moderate number of carbons involved. Here's sort of, again, a table of solubility, and we do see as we kind of go from like upwards of 5 carbons, very, very soluble, again, with very little carbons on the left-hand side in all these cases. The waters are able to really interact well with this group. But, as we start building out a lot more carbons, we get something like I mentioned before, sometimes referred to as steric hindrance, which basically means this big non-polar part here kind of gets in the way. And, even though there's still this polar aspect of this molecule, it really just gets in the way as water tries to sort of make its way through. It's like, I don't really want to participate with you. And, I can interact with this part of it, but, you got this big non-polar part. Remember, in order for things to be soluble in water, essentially, you have water attached to waters, right, before you kind of put anything in there. So you have to kind of break these water bonds and replace it with something very similar. And if you start building out a lot of carbons on the back end, you get these really big molecules that does not fit very well with like small water. And that's why we start to see a decrease in solubility again as you go above that sort of 5 or 6 carbon threshold. but up until that point, pretty good in certain solubility, and again, has a very high boiling point and melting point because of its ability to hydrogen bond. Carboxylic acids are pretty much what they sound like. They are acids, which means they tend to react like acids. A lot of them are weak acids, like acetic acid, which is this guy right here. Weak acids, as we talked about in an earlier chapter, are basically weak electrolytes, which means basically it can be in solution and set up this equilibrium where we have this ion that's present and we have what is referred to as the protonated form, but basically the acid here. And in solution, mainly this is what we got going on. We do have a little bit of this guy form like we talked about, but because they're basically acids, they basically can behave very much like an acid-base reaction is typically what happens, especially when we do get a base involved. They do a basic sort of acid-base sort of reaction that occurs. But they will set up these reactions here. For example, here, if we look at butanoic acid, again, 1, 2, 3, 4 carbons, carboxylic acid group in water, really going to act as an acid. So what does that mean? An acid, if you remember, is something that will donate over an H+. When it donates over an H+, pretty much everybody here remains the same, except that we lost the H, right? So that's what this comes from. And just like we talked about with Lewis acids and bases, the H is not just the H by itself, but it is the plus, which means we then become one more negative, which is why there's a negative charge there. Obviously, the water picks up that H plus and makes H3O plus, which is what we see over here. So this sort of guy here is pretty identical to our Bronsted-Lowry definition of an acid, and water here acting as a base in this particular case. Any questions on that there? Now, like I mentioned before, since it is also an acid, it could basically react with a real base, if you will, like a strong base. So we can also see a reaction of a carboxylic acid with a strong base like sodium hydroxide or potassium hydroxide. And if you remember, this also is really going to be just the same reaction we've seen in acid and bases. This is an acid plus a base. And if you remember, when you take an acid plus a base, you basically get two things. You get a salt and water. Salt really just being an ionic compound. And where does the water come from? It comes from the exact same place we talked about that reaction in acid and bases. It is the H from the acid. It is the OH from the base. And that is where our water comes from. And then basically when that acid loses the H+, it becomes negative. And obviously this sodium is really sodium with a +1 charge, which is what we have here. That really makes an ionic compound. And this is what is referred to as a salt. This is sometimes what is referred to as a carboxylate salt because it comes from a carboxylic acid. So this is what is sometimes referred to as carboxylate salt. You don't have to worry about naming this guy here, but this is, again, what happens. So this is, again, our salt and water being formed. So the good news is sort of carboxylic acids do pretty much the acid-base reaction, just like we talked about in the acid-base chapter there. And again, same thing happens. H from the acid, OH from the base makes the water. And then you basically just put together the other part, which is going to make an ionic compound. Even if it's hooked up here to, even if it's really hooked up here to a benzene ring, same idea. This is our acid, so it's going to be the H from the acid, OH from the base, again making our water and our so our acid, our base, and again making our salt and our water in this case. And you can see that the carboxylate ion is named by replacing the ic acid with 8, and this is potassium benzoate. And again, it comes from basically replacing this part of it and put 8 at the end of it, We're not going to probably name too many of these salts, but that's sort of how the name comes from. It's really kind of like an ionic compound. This is potassium, and this is, again, benzoate, coming from that benzoic acid. What are carboxylic acid salts? They are basically ionic compounds with really strong attractive forces because they are ions. They typically are solids at room temperature. They have high melting points and usually are soluble in water because really they're kind of an ionic compound in this particular case. So here are some examples of some carboxylic acid salts. They basically all come from really the reaction of a carboxylic acid with a strong base. Since we see sodium here, we could probably make a pretty good prediction that they were all reacted with sodium hydroxide as a strong base. And if you wanted the carboxylic acid that this came from, you basically would just put back on the H at the end there. That would have came off, and this is again propanoic acid, which is again where this salt basically are evolved from. Basically, those two guys will make this guy here. Same thing here, again, benzoic acid. And this is actually a little bit different. It's a couple of different carboxylic acid groups on top of this guy. You don't have to worry about that guy in terms of names or anything like that. And in general, you probably don't have to worry about, like I said, the names of the salts that are formed. You do need to know that they are formed and sort of how to draw them, but you won't have to basically worry about naming them. And here's some of the ones we just looked at there. Sodium benzoate inhibits sort of growth of mold. MSG was added to meat special fluid as sort of an enhancer as well. So again, if we look at this reaction of carboxylic acid with sodium hydroxide, propanoic acid, again, we would, if we wanted to draw it, propane means 3, oic acid means carboxylic acid. And at this point, we would fill in our hydrogens. We would react that with sodium hydroxide, again, a acid basically and base. We're going to pull our water out of there, which are these two guys. And what's left, again, we could kind of follow the same thing we've been doing, pretty much just draw what's here, because that's pretty much what's left over. Remember, when we lose that H, it's an H+, so we become one more negative, and the only other thing left is our sodium ion, which is where our, again, carboxylic salt basically comes from. Any questions on that reaction? And there you go. That's what we just drew, so that looks good in that case. So they are obviously, as you can see here, part of the metabolic sort of process within our cells during glucose. The molecule of glucose broken down into pyruvate, carboxylic acid salts, and pyruvic acid, as you can see here. If you take some of that biochemistry and stuff, you'll learn about the Krebs cycle and all that kind of stuff. Not really important for us here in this class, so you don't have to worry too much about it. These, again, just to look at some of these guys that are in that cycle, but just to kind of tie it to what we're talking about, again, each of these guys here are carboxylic acid groups, basically, and you can see there's actually 2 of them on each of these guys in that sort of Krebs cycle. All right, any questions on carboxylic acids? So essentially, it's an acid. It could act sort of as a Brodsky-Lowry acid and base. It also can react with a strong base, basically to make a salt and water in a typical sort of reaction. Any questions on any of that? Okay, then let's talk about esters. Esters are another organic chemistry group here. They are sort of built from, as we'll talk about, really a carboxylic acid and an alcohol, which means their functional group kind of shares some of that. We have the carbon-oxygen double bond to the oxygen. The difference here is in a carboxylic acid, we have a hydrogen here. We actually have it connected to a carbon. So this is sort of the functional group, or connectivity that occurs in an ester. Esters, as we'll talk about, basically are a lot of things that are responsible for a lot of sort of flavors or odors that we sort of associate things with. When they are made, they do produce some of these sort of odors and smells and so forth. Esters are basically made by a reaction of a carboxylic acid and an alcohol. And that reaction, as we will see, is what is referred to as an esterification reaction, which is a fancy word to say I just made an ester, basically. And again, it doesn't really matter what your carboxylic acid might look like. We'll just draw one here. That looks good. And basically, you could react it with an alcohol, and I'll just draw the alcohol this way. And basically, when we do this sort of esterification reaction, as we'll see, we're basically going to take out water, basically. So we're basically going to remove water, and we're going to basically remove water as follows. Going to make water from like the OH here on our carboxylic acid, and our H there on our alcohol. So we take our carboxylic acid and our alcohol, pop out water there. And then pretty much what we do is just squish them together. So we're going to go from the left-hand side to the right-hand side. And again, the only thing we're not going to do is obviously draw the water part in there. So we're just going to simply draw exactly like it is. Again, as we talked about, nothing weird happens in this situation. I'm taking out the water, which means my new connection point is right there. That gives us our ester kind of connection that's happening. And just continue up over here. So we make this ester from an alcohol and a carboxylic acid. Any questions on that there? And again, this is why it pretty much has a functional group that looks very much like carboxylic acid, because that's essentially kind of where it comes from. So here again is that reaction, same deal. We're just going to kind of pop out the water here. And at that point, absolutely nothing changes. We got our CH3. We have a carbon-oxygen double bond, carbon-oxygen double bond. Obviously, we skip what's in the box, go to the oxygen next, and go to the CH3. So it really is an esterification reaction, not too bad. Basically pop out the water and then just kind of squish both sides together. So sometimes it's helpful when you have the alcohol part, if it's not necessarily maybe not necessarily drawn with the OH group facing it. Sometimes it's helpful just to kind of rearrange it, if you will, and flip the alcohol around where the OH group is sort of facing it. And then it makes it maybe easier to visualize taking out the water and then what you're going to basically squeeze together after you take out the water to make your ester. So sometimes it's helpful, if it's not necessarily drawn that way, flip it around and you can kind of visualize sort of what is happening in that particular reaction. Any questions on that one there? Okay, why don't you, actually, here's one right here. So here's a, excuse me, an example of an ester here. Again, our water again coming together and putting it together, making our ester bond, which is basically right here, that connection, right? That's that connection that basically makes the ester. And it's that basically, just so we're clear, going away from the carbon-oxygen double bond, away from the oxygen there. That is the carboxylic acid part. Going towards the single oxygen, away from the double bond, is our alcohol part. And that's sort of important, that part of it, which part is the carboxylic acid part, which part is the alcohol part, in terms of how you go about sort of naming these guys. when we get to naming here in just a second. So let's see here. So why don't you take a second here and try this one. Why don't you write the reaction between propanoic acid and methanol in the presence of heat and an acid catalyst and see what you come up with. And while you're doing that one, why don't you also do this one? All right, so I want you to do the question here, and I want you to do also this one here. Draw the product of what you come up with. We'll start with the one in the words here. So we want to make sure we get the right formula. So propanoic acid, I know it's a carboxylic acid because I see the oic acid part. Propane means 3, so again, that's where we'll start. We will put our carboxylic acid group, which should go on the end. You could draw it on the left-hand side or the right-hand side because you're drawing, so you could go either way. And that would be our propanoic acid. Methanol is based off of methane, which means it's a 1-carbon alcohol, which has something like this here. So in this case, again, you can see I drew it so that the HO and the OH kind of line up to each other. Again, just sometimes it helps visually to make sure you don't get things sort of backwards and stuff like that. You obviously could write the alcohol like this too. It's perfectly fine. But by doing this, again, we could just kind of put a box around our water, which we want to take out. And that at that point, when we do that, we now have everything sort of lined up the way we need it. We really just start left to right, obviously skipping the box part. And we're just going to squeeze everybody together there. So CH3, CH2, C double bond O. I'm now going to move out the water part and pick it up on the other side where my alcohol part, again, going towards the single oxygen is the alcohol part, going towards the double bonded oxygen and away from the single guy, again, our carboxylic acid part. Any questions on that there? Okay. Now, in this case, I didn't really line it up kind of back to back, so you can flip it around if you want, or, really know that it is the OH here and the H is going to come off. The important part, though, is to realize that the connection point is the oxygen, because I can tell you a lot of people will just connect it into the carbon here. So that's why I say sometimes maybe it's better to flip it around so you could visually see it. But here we would do the same thing. I'm just going to draw it down here since I ran out of room on the right there. But we'll go this way, which is our water. Now I'm just going to start here on the left and work my way over. So that's CH3, CH2, CHCl. Again, nothing changing. So that brings me to here. Again, I'm going to take out the water. I'm going to take out the hydrogen to make the water. Again, important, not going to connect here, but it does need to connect at the oxygen, which means we should have the oxygen, the CH2, CH2, and CH3. Again, remembering that this is really our connection point here for an ester, and same deal. Going towards the single bond is where our alcohol comes from. And again, going away from it is where our carboxylic acid comes from. Any question on either of those there? And again, if it helps you better visualize and not going to make the wrong connection here, flip the alcohol around and put the OH, next to each other. Any questions on this reaction? This is an esterification reaction. It is basically how we make an ester. Carboxylic acid and alcohol makes that ester. Any questions on that there?
How would you name that?
Actually, that's the next thing we're going to talk about right now. So if you hold on, I think we'll get right to your question. Other questions on that?
Okay, then let's talk about how we go about naming these guys. So how we go about naming these guys, as I just mentioned a second ago, there's really two parts to our ester, right? There's the part that comes from the alcohol, and there's the part that comes from the carboxylic acid. So that's why on the last ones and stuff that we've just been drawing, I try to emphasize the idea that, the connection is sort of here, if you will. And again, knowing that going away from the double bond is the alcohol part, and going like through the double bond, if you will, or away from the single bond is the carboxylic acid part. It's really important for actually the naming aspect of it. And that's because the alcohol part, or really the part that comes from the alcohol, it's just named like an alkyl group. So this part here, which comes from the alcohol, has really just a one carbon group. One carbon group is basically a methyl group, and that is where that part of the name comes from, methyl. The other part comes from, again, the carboxylic acid, which is going from the double bond away from the single bond this way. And if we look at this guy, there is two carbons basically there. And those two carbons are based off of ethanoic acid. And basically we drop the, however you want to think about this one, you could drop the OIC acid, if you will, and put O8 at the end of it, or you could drop the IC and put 8 at the end of it. But basically it ends in O8 like that. So this becomes ethanoic. So this is methyl for the alcohol part, ethanoate. Basically two carbons on the carboxylic acid part. So really important with esters, again, to be able to identify, which group it's coming from. And although a lot of times we do see it drawn like this, you could have an ester drawn just like this. So it doesn't necessarily mean it's always to the right is the alcohol and to the left is the other guy. In this case, it would be the opposite. Again, going to the single bond is the alcohol. And again, going towards the double bond is the carboxylic acid. So I don't want you to get into the habit of thinking, well, alcohol is always drawn to the right and, the carboxylic acid is always on the left. It may not be. So that's why it's important to understand sort of where it breaks and which side basically is the alcohol and which side is the carboxylic acid. So you could actually think about the oxygens if it helps. Going towards the single bonded oxygen is the alcohol. Going to the double bonded oxygen is the carboxylic acid. So alcohol has one name, so single bonded oxygen, carboxylic acid, two names, double bonded oxygen side. And that's a way you could kind of remember how to do that. So basically alkyl name like methyl, ethyl, propyl, butyl, all those type of guys. And then basically alkane name, if you will, drop the E and put O8 at the end of it. And that basically is how you go about naming this guy. So if we look at the ones which was the question which just asked, which is, how we might go about naming some of these guys here. For example, here, looking at this one, this is our going to our single bonded part, like we talked about, the alcohol. That is going to be methyl. Going the other way, 1, 2, 3, which is going to be propanoate. So this would be methyl propanoate in that case. Any questions on that? This guy would also be named very much similar. You got your propyl group here, right, which is our alcohol group. This one might be a little bit trickier because we do have this extra guy hanging off, which technically would be 1, 2, 3, 3 chloral, 1, 2, 3, 4, 5 pentanoate. So this would be propyl, 3 chloral, pentanoate. So you would have to sort of add that chlorine in kind of from the carboxylic acid name as well. A lot of times they don't really have that extra kind of guy hanging off. I just kind of threw it in there, but that's sort of how you would incorporate that name into it. Question on that there. So let's take a look and again, see how we get to these names. So going towards the single bond is oxygen. is our alcohol name. So we see 2 carbons, which is, again is the ethyl, going the opposite way away from the single bond towards the double bond. Also 2 carbons, from ethane becomes ethyl ethanoate. Again here, carbon oxygen double bond going away from the oxygen, the single bonded. It gives us our carboxylic acid name. That's based off of propane, becomes propanoate. And again, going in the opposite direction there, going towards the single bond, we have 1 carbon, which is where our methyl name comes from. Same thing here, single carbon alcohol part, 2 carbons ethyl. Going the other way, we have our really benzene ring this way, right? Which is from benzoic acid, becomes basically benzene benzoate. So ethyl benzoate. Any questions on how to go about naming those guys there? So let's take a look here. What we got here. So salicylic acid is basically aspirin, and you can see it is a carboxylic acid, as you can see here. And you can make an ester by doing that with acetic acid. Same reaction, even though it may look scarier that's sort of happening, we do sort of actually take the alcohol group here and this guy going to come together to make basically acetylsalicylic acid, which is basically aspirin, as the reaction of salicylic acid and acetic acid together, basically vinegar and salicylic acid gets us basically aspirin. And again, we actually have the ester bond here, carboxylic acid group on this guy. You don't have to worry about drawing that. I'm not going to actually ask you to do that one, obviously. But why don't we try this one here? Why don't we name this ester? So see what you come up with. Take a moment and see what you do. And while you're at it, let me just draw maybe another couple here. Let's do. Okay, why don't you name all 3 of these, see what you come up with. Okay, so let's take a look at it. So hopefully, again, we can recognize that each of these are obviously esters. We see our functional group. Best approach, again, is to remember there's the 2 parts. You can literally just draw a line between that connection point, which is always the carbon-oxygen single bond. And again, an easy way to remember is if I go away from the double bond, that is the alcohol, which obviously means the other way is the carboxylic acid. That's important because that's the first part of my name, which is the alcohol part. And that is 2 carbons. So 2 carbons is basically an ethyl group. Now going the opposite way, I have 1 carbon, 2 carbons, and important not to forget the carbon that's sitting there on the double bond. Again, another very common mistake that people forget to count that carbon. That's 1, 2, 3. 3 is based off of propanoic acid or propane, and it becomes propanoate, O-A-E, O-A-T-E. So this would be ethyl propanoate. Any questions on that particular one there? All right, so again, same deal. You could go and go, okay, this is my ester, this is my connection. I know if I go away from the double bond, that is the alcohol part. If I spell alcohol right there, there we go. So again, doing our first part of our name, which would come from the alcohol part, that is 3 carbons. 3 carbons is a propyl group, I believe still. I know now going in the opposite direction, that is the carboxylic acid part. And again, I just want to make sure I get all the carbons, including that one on the double bond. Gives us 1, 2, 3, 4, 5, 6, based off of hexanoic acid or hexane. and you could just put the OAT at it. This would be propyl hexanoate. Any question on those first two names? Looking at the last one, again, this is our ester connection, and this is why it's important to know which way you need to go, because if I went to the right, that is not the alcohol part. Again, I need to go away from the double bond for the alcohol part, which means the alcohol part is actually over here. And that is a 1, 2, 3, 4 carbon group. 4 carbons is a butyl group. Now coming to my carboxylic acid, which includes that carbon. That is 3 carbons, which again would be propanoate. So butyl propanoate. Any questions on the naming of an ester? So again, really important to know sort of which way is which. And if you want to keep it simple, you could do what I just did here. Draw a line between the carbon-oxygen double bond, draw an arrow going away from the carbon-oxygen double bond, and that's always going to be your alcohol part going in that direction, which then by default means the other part is your carboxylic acid part. Any questions on naming esters? So here, if we look at this guy here, I don't think that was one of the ones we named, was it? I don't think so. Let's take a look at this guy again, following the same thing. We see our ester. We're going to, again, draw our line where it comes together. We want to go away from the carbon-oxygen double bond, which will give us the alcohol part and the first part of the name. Again, looking here, that is a 3-carbon group, which is a propyl group. Going in the other direction, going to give us our carboxylic acid name, which is basically ethanoic acid or ethane. Again, if you want to go with ethane, drop the E and put the O8 at the end of it, you can, and that would be propyl ethanoate. Any questions on that particular one there? All right, so esters, as I mentioned earlier, they really have a lot of sort of fragrance. They're responsible for a lot of fragrance of flowers and flavors of fruits. They're due to esters. Small esters are volatile, which means they can, if something's volatile, it basically is a fancy way of saying it could go into the gas phase very quickly. It could go into sort of the vapor phase, which if you sort of think about it, that means obviously you'll be able to smell it, right? If it goes into sort of the gas phase. Hence, I think why she's smelling the pineapple, I think, in that particular case. And here are some of the esters here. And again, if you look at all these, we got our esters coming in here, our connection right there, making our esters. And again, in all these cases, going to the right are the alcohols, basically. And you can see the guy up here, propyl ethanoate, is responsible for sort of pears. We got pentyl ethanoate, which is bananas, oranges, octyl ethanoate, again from octanol, basically, 1 octanol, and pineapples here for ethyl butanoate, apricots, and so forth. Again, all these guys are made up of those two things, a carboxylic acid and an alcohol. So let's make sure we know how to draw some of these. So why don't you draw that guy there, 3-bromol butanoic acid, ethyl butanoate. Why don't you also draw, put a couple more up here for you. All right, why don't you draw the structures of these guys, see what you come up with. Okay, so again, remember, like any organic stuff, that when we go to draw it, we want to make sure you kind of work backwards. So obviously here we do see oic acid, and again, when we do see that, that should scream carboxylic acid, which means I should have this functional group happening there. Butane basically is that back part of the name. So butane is basically 4 carbons, which would be where I would want to start. That's 4 carbons. Since you are drawing, as we talked about, you can again put that whichever way you want to go, on the left-hand side, the right-hand side. I'm going to just put it on the right-hand side. Again, you could absolutely put it on the other side if you wanted to. Because I chose to do that, remember that this carbon is going to be carbon number 1, which means when I go for my 3 bromol, this would be carbon 2, and this would be carbon 3. That is where I need to put my bromine in that case. At this point, like we've done before, everybody else is going to be hydrogen. So guy at the end needs 3. Guy here actually just needs 1. And guy here needs 2 in this case. And there we would go. Any questions on that drawing right there? Looking at the next one, again, at the end of the name, I see O8. So O8 tells me it's an ester, which means that I know for sure, because I know my functional groups, that I should pretty much have this sort of connection happening. So working with that, remember that the end part of the name is really the carboxylic acid part, which means propane is 3 carbons. So in this case, I may want to actually start with that connection. Remember that going away from or through the double bond, right? Away from the single bond is the carboxylic acid part. So I should add 3 carbons there, right? Going this way is our carboxylic acid. We already have a carbon here. Coming the other way is ethyl, which comes from the alcohol part, which is definitely going away from the carbon-oxygen double bond. And in this case, we would have ethyl, which is 2 carbons as well. And there we go. And at this point, we just need to fill in our hydrogens. So we need a 3 there, 2 there, a 2 there, and a 3 there. Any questions on that? So doing the same sort of approach for our next one, that's O8, which is our ester. Again, probably want to start with that connection point there. The hexane part, again, going to come from the carboxylic acid, which is actually going this way, right? Sort of away from the double bond there, away from the single bond, away from all the oxygens, basically. And that's going to be 6. We don't want to forget we already have a carbon there. So that would be 2, that would be 3, that would be 4, that would be 5, and then that would be 6. Pentyl will come from the alcohol part, which is going in this direction, right? Away from the double bond towards the single bond. And pentyl is 5 carbons. 1, 2, 3, 4, 5. Should have picked less names there, but we then want to put in some hydrogens. So 2, 3 there, 2 there, 2 there. We'll go with 2 there, 2 there, 2 here, 2 here, 2, 2, and 3 at the end. Any questions on that one? Lastly, doing the same approach again with our O8, going to start with our connection here. And again, if you want to mix it up, you could start with the propyl, but we can still go our correct way here, which is pentane. Again, doing it to the carboxylic acid part and going upwards so I don't run into the name. 1, 2, 3, 4, 5 carbons for the pentane part. Propyl come in the alcohol part, which is where the carbon-oxygen single bond is. 3 carbons in that case. Again, now we're ready to fill in hydrogens. It's like 2's all the way around, except for the last guy, which should be 3 in this case. Any questions on how to draw esters or how to draw carboxylic acids? So again, with this one, because there is that sort of connection, and one way is the alcohol, one way is the carboxylic acid, it's sometimes good to start with that and just remember away from the double bond, going where that connection is, we're going to go to the alcohol part, right? Any questions on any of that there? Okay, so the next thing we're going to talk about with esters is some reactions that basically esters undergo, and they're sometimes referred to as hydrolysis reactions. Hydrolysis reactions basically means somewhere along the way, there's water involved. Yeah, so water obviously is a key one. You could probably imagine that because when we made an ester, we basically took water out. So when we made an ester, for example, like this guy, with a little bit of acid as a catalyst and some heat, which is what the delta symbol means, we basically took the water out. And as you can see, when we squeeze it together, we got our ester through our esterification reaction. So there's a couple of different types of hydrolysis. One hydrolysis is basically just the reverse. We're just going to put the water back in and it will break it back apart into its carboxylic acid and its alcohol. So it's covered the reverse reaction of a esterification reaction. And that actually is what is referred to as the acid hydrolysis. The acid hydrolysis basically means that it's going to be done with an acid catalyst, which is what the H plus here on the arrow means. Remember, a catalyst really is just something that will speed up a chemical reaction, not used up, not really a reactant or product, just there to facilitate the reaction occurring. Remember, heat is also sometimes displayed with a triangle sort of symbol or delta symbol. So when we do this, pretty much what happens is we kind of break it back apart the same way-ish, if you want to think about it, how we kind of built it together. It's not exactly maybe 100% correct how it comes back together. But since we think about it breaking here, it's a good way to think about it as well. So in this particular case, what's going to happen is alcohol is going to come off this way. Again, carboxylic acid is going to come off this way. And what you will get is actually both the completed carboxylic acid back and the alcohol back. So again, you may be saying, how do I know sort of what happens? So you just want to kind of do it in reverse of how we put it together. So when we would look at this and we're going to add water here with our acid sort of and some heat, what's going to happen is, again, you could just put the line right there where we know it comes together, where it makes sense it would break apart. And you could really just start to draw, I'll put the arrow down here, your two parts. So I know this is one of the parts, and I know this is the other part. And I know my water is basically H and OH. So I know I'm supposed to get a carboxylic acid, which comes from this part, right? So what will get me to a carboxylic acid here? I need to add the OH, right? And I know I get an alcohol, which comes from this part, right? The alcohol. What am I missing to make this an alcohol? Well, it would be the H, right? So I'd put the H back on here. And now I have back again my carboxylic acid and my alcohol. So in an acid hydrolysis of an ester, you will get the completed carboxylic acid back and also the completed alcohol back. Basically, we're just throwing water in. It's basically the exact reverse, if you will, of a esterification reaction. Any questions on that reaction? We can also do this same sort of hydrolysis, but in what is referred to as basic conditions. And this is really sometimes referred to as a Sephonification reaction, which is a big way of saying soap. So it's sort of how we make soap. Taking an ester like this, but usually it's an ester that has when you really sort of make soap, a ton of more carbons, a lot of carbons going on. So really in sort of a
soap situation, a real soap situation, you would have a ton more carbons hanging out there on the carboxylic acid side. So what happens in this case is very similar to sort of what happens in the acid hydrolysis, except one thing. We're sort of, if you will, missing like the water part of it. We're also missing the acid part. The acid part also provides a lot of H plus in the solution. So we're sort of short that. So that has an effect on sort of what's going to happen here. We're actually going to get our alcohol back completed, but we'll actually end up with the carboxylic acid salt instead. So you can still think of this the same way, like I'm going to split it here. In the base part, which is this way, I'm going to get my alcohol back. So basically what that means is if you think about it, we're going to take the H and pop it back onto that guy, just like that. On the other side, we have this that's left over. And if you just want to kind of keep track of it, if you think about what we have here, we got like an Na plus, we got like an O, and we got like an H. We kind of use the H, we have an O left, and then Na plus, the oxygen's actually becomes negative, and we actually will get the oxygen back. But again, we're missing that extra hydrogen to make it a completed carboxylic acid. So this is basically what makes sort of like a soap or that carboxylic acid salt. So here we get salt and an alcohol back. We don't get the completed carboxylic acid. So that's a major difference between those two reactions. Acid hydrolysis, you basically get back the completed carboxylic acid and the completed alcohol. If you do the base reaction, you actually only get back the completed alcohol. You get almost a carboxylic acid back, missing the, as I put up here, H plus that we're short. You basically get that carboxylic acid sort of salt. Any questions on that one there? Okay, so let's take a look at one here. Write a balanced equation for methyl acetate. This is also what is known as methyl ethanoate. Acetate comes from acetic acid, which is a common name. Acetic acid is ethanoic acid. So this is methyl ethanoate. So why don't you try that? We're going to do the methyl ethanoate. Good idea to draw that too. And you want to know what happens with the acid hydrolysis and what will happen if you do the base hydrolysis, which is the bottom one. So why don't you take a second and see what you come up with. In this case, KOH being a strong base.
Could work through this. Obviously, we want to start with the correct formula there for methyl ethanoate. Again, a reminder, as I mentioned just a second ago, methyl acetate again comes from really acetic acid. And remember, acetic acid really is ethanoic acid. And again, that's a very common name that we talked about, I think, the other time, that they're sort of used interchangeably a lot. So methyl ethanoate, again, we see the O8, which tells us we are definitely starting with the ester. So we want to start with our connection here. Again, double bonded side away from the oxygen is where our ethane part, which would be 2 carbons, and our methyl would be the alcohol part, which is on this side. Again, filling in our hydrogens will look something like this to begin with. First off, any questions on methyl ethanoate? This is going to be our water, which we can kind of think about like this, and our heat and acid, which sometimes catalyst, which is written on top of the arrow, and again, heat sometimes like that. So the way to remember it is, if you want acid all, AA all, So all means I get back everything I started with here when I do this sort of reaction. Again, the easiest way to sort of think about it is just to split it where it connects. And remembering that, again, going this way is our alcohol, which means by default going this way is our carboxylic acid. And since it's the acid, which means I get everything or all of it back, we could just basically draw the parts and complete out, what we need, which means this is our carboxylic acid, which means it's missing an OH. So there we go. This is our alcohol, which means it's missing an H, right? So there you go. We now got back the completed carboxylic acid and the completed alcohol. Any questions on that particular one? Now, starting with the same guy here to begin with. This is different though. This is going to be our base hydrolysis, which means we're not going to get everything back. We are going to get our alcohol back, we know. Might as well approach it the same way. We're going to basically break it right there. We're going to draw our parts like we did before. And again, we can know, just like before, we will get that completed alcohol back. So if you want to just cross it off, there it is. This oxygen actually becomes negative, and that goes here, which gets us almost our carboxylic acid, but it doesn't. It becomes something with a charge, and potassium is +1, and that gives us our salt that happens here. So our salt and our alcohol, our carboxylic acid, and our alcohol. Any questions on those two reactions? Okay, any questions on esters there? Okay, then we're going to talk about another organic group, which is actually a nitrogen containing group, and those are amines. Amines are really ammonia derivatives. So if you remember, ammonia is NH3. So the functional group of an amine really is this guy right here. That's the functional group of an amine. It's a nitrogen with maybe one hydrogen, maybe two hydrogens, maybe a few more hydrogens or less hydrogens, but they're all basically sort of derivatives of ammonia NH3. And we could actually classify amines just like we classify carbons, just like we classify alcohols, as there's primary, secondary, and tertiary amines. But if you look here, you could kind of see, they all are sort of a nitrogen containing group. This guy has a couple of hydrogens. This guy's got one hydrogen. This guy's got no hydrogens there. And again, these are all basically amines with that nitrogen containing group that's involved. As I mentioned before, we could classify them as primary, secondary, or tertiary. And how do we figure out primary, secondary, or tertiary amines? It's very similar to sort of what we do with everything else, but a little bit different. Here we're actually looking at the nitrogen and how many carbons are attached directly to the nitrogen. So in this case, there's only one carbon that's attached directly to that nitrogen, makes it a primary amine. Attached to this nitrogen here is one carbon there and two carbons there, makes it a secondary amine. Attached to this nitrogen, one carbon there, two carbons there, and three carbons there, makes it a tertiary amine. So a little bit different than some of the other guys that we've done before, but in this case, we want to look at the nitrogen and how many carbons are directly attached to it. Question on that there. So obviously here, if we looked at this guy, 1, 2, and 3, that would be a tertiary amine. If we looked at this guy, it actually has one carbon attached. It would be a primary. And if we look at this guy, it has 1 and 2 carbons attached, would be a secondary amine in this particular case. So again, we could definitely classify these guys by primary, secondary, or tertiary. Also has a little bit of effect on sort of how we go about naming them. Any questions on that sort of classification there? So let's talk a little bit about how to name amines. Simple amines are named with the alkyl group, and then you basically just put amine at the end of it. So for example, here we list the names of the alkyl groups bonded to the nitrogen in alphabetical order, and then basically just put amine. Use prefixes to identify multiple groups. So what does that basically mean? If we look at this guy here, we see the nitrogen group, which tells us it's an amine, and we see a 2-carbon group attached to the nitrogen. 2 carbons is ethyl, and it's an amine, so ethyl amine. Attached here to the nitrogen, you could kind of go to the left, which is a methyl group, to the right, which is a methyl group, and that is where we get our dimethyl amine. This is kind of like the ethers, where you go to the oxygen, go to the left, go to the right, and you kind of do your groups attached there in alphabetical order. Here we have to the left a methyl group, and an ethyl group, and that is ethyl dimethyl amine. Remember, alphabetical first letter, not prefix, so that's why the E came before the M in this particular case. If we look at each of these are the 3 different types of amines. This is a primary amine, secondary amine, and tertiary amine. Any question on those guys there? Now, this is sort of the way they show you to name these guys, and this is, I would say, more of a common name way of naming it. And so, for example, ethylamine would be correct. You'll sometimes see people name this, for example, we'll look at this here, this guy here, and well, sometimes people will name these amines a little bit different. They will take sort of the longest carbon chain that's attached to the nitrogen. In this case, it would basically be ethane. They'll drop the E and put ethane amine at the end of it. And now you may be wondering, what would we do with these groups? Normally in a carbon chain, we would use numbers, right? Like 1, 1, or 2, 2. In this case, these groups are not attached to the carbon, but they're actually attached to a nitrogen. So you'll sometimes see people, instead of using a number, go N, N dash dimethyl ethane amine. The N means that the methyl group is on the nitrogen, also means it's on the nitrogen. So sometimes you'll see this sort of naming happening with both secondary and tertiary amines. But for us, we'll go with this type of naming as the way to do it. But I just wanted to show you again, you may actually see something named that way. You may be wondering, like, what does the N mean? So the N in this case, and it happens with amines, also happens with amide sometimes. The N means basically that the alkyl group is attached to the nitrogen versus a carbon in the chain. So again, this is I just wanted to show it to you in case you happen to come across it somewhere. That's another common way. But for us, in terms of naming, we'll go with this way of naming for amines for exams or anything like that, that we'll go with those guys in that case. Any questions on that there? Okay, why don't we finish up with these 2 here? We want to write the common name and also classify each of these amines. So see what you come up with here. To the end here is take a look. So we'll go with that sort of common way of naming. So we basically go to the nitrogen. We try to find the group that's attached. In this case, it is a 3-carbon group, which means this would be propyl, and then we would just put amine at the end of it. This also would also be a primary, as there is just 1 carbon that's attached to the nitrogen. Any questions on that one there? This one is, I think, the same one that we just looked at, probably. I think on the last page, it kind of looks the same. But just to make sure, if we just kind of go around the nitrogen and boxing off our groups, that's an ethyl group. That is a methyl group. That is also a methyl group. And I believe it is the same one as we just saw there. So that's going to be ethyl. Again, dimethyl, alphabetizing E before M, ignoring the prefix like we talked about previously, and then amine, and it is still as same as the before, 1, 2, and 3 carbons, which means it's a tertiary amine. Any questions on that there, or anything we talked about here today? Okay, so let's just make sure everybody's on the same page here before we say goodbye for the evening here for lecture. A reminder, on Wednesday, there will be no lecture as we are taking our last exam 3, which will cover those 2 non-organic chapters, so solutions and acid and bases, and the 2 organic chapters, not including this chapter we're currently